Let's create a network data set for driving. Firstly, have a look at the CAN-RTE attribute table. Since CAN-RTE is the one in the driving geodatabase. This is a subset of DMTI's CAN map route logistics. And you can download the entire DMTI CAN map route logistics network data set for all of Canada from the Scholars GeoPortal. Again, to do so, if you wanted to do anything with that, you have to be authenticated on campus. Using the library, for example. Otherwise, you can't download anything from Scholars GeoPortal. It's only available to Ontario. So here we have ONEWAY. So that's a field in the table right here. And that specifies the ed direction of travel. This means because there is ONEWAY, we will have a not an undirected, but a directed graph. So we'll have a directed network where some streets only have one direction of travel. We have the speed limit as well for every edge. That means every road. We have a from to and a to from minutes, which is the time to travel in one direction on the edge and the time to travel in the other direction, because those can differ. We have the elevation fields here, something we didn't have when we made the walking data set. The elevation fields are fundamental because, again, that will tell you whether or not a particular edge, when it crosses another edge, if there is an overpass or underpass. If there's an over or underpass, then there's not a node. No node would be created in a case like that. Otherwise, nodes are created and an agent traveling here could go that way, or an agent traveling this way could go that way at that junction. Whereas if we have elevation, it's more like this. And so an agent traveling in this direction cannot jump up onto the overpass. They can only go straight here. Likewise, an agent traveling here can only go straight because there's no junction there. And only at junctions in a network, if one was present, could directions change on the network. And that can make a big difference in driving directions, obviously, or say driving travel time. Because you could potentially live right beside a major route, let's say like the 417 in Ottawa. That's the major route that goes through Ottawa. But you may still have to drive 5 or 10 minutes to find an on-ramp, because 400 series highways are controlled access. So not every street that would go and intersect Highway 417, let's say there's one going here, can possibly get onto Highway 417 through a junction. It's not possible, since you have to have a cloverleaf access ramps for getting on or off the 417. So elevation allows that type of flow in the network to continue in one direction or in the other direction without being able to change directions at junctions, because there would be no junction there if there's an under or overpass. We also have road classes. So higher class versus lower class roads. So like 400 series highways, for example, versus 100 series highways versus residential streets. And each of these has different meaning. So 400 series highways are controlled access, 100s aren't. You know, you can get right onto a 100 series highway but you can't get onto a 400 series highway. Then we also have hierarchy. And hierarchy classifies network edges into preferred travel. And that helps in solving certain problems. In other words, a hierarchy of 5 is less preferred than a 1, or less preferred than a 4. A 3 is more preferred than a 4. A 2 is more preferred than a 3, and a 1 is more preferred than any of the other ones. So these are the tables, or this is in the table, I should say, these are the fields or columns in the CAN route table that are used in creating the driving network. So just like the walking network, we would go to the OT roads feature dataset, new network dataset, and then we can use the default name. Here we have one thing participating. So on the next screen, it's just participating as one participant. Feature class. So we have one participating feature class, which is CAN RTE. We don't have a multimodal network here for driving because we can't drive from a street to a trail. The trails and paths, you're not allowed to drive on. And then do we want to model turns? Definitely. So we want that slight time penalty to be taken into account for a right turn versus a left turn. Connectivity, by default, it'll be fine, but you can also check it out that it's at endpoints only. So this is a data set that's made for driving, and so the connectivity will automatically go just to the endpoints, not to any junction. Then, how do we want to use elevation? Well, we just have to see here, it'll automatically be chosen for us because ArcGIS knows that these two fields, FZ11 and TZ11, are field names for elevation fields. And so we'll automatically find those for us and set them up because it knows that those are preferred field names for that type of thing. And again, that gives the overpass, underpass idea. That's what this little graphic is showing here, the elevation field. Then we get to the network attributes. And we look at hierarchy, for example. So hierarchy is one that I just mentioned a couple minutes ago. And it'll automatically be put in there because it knows that a hierarchy field means a hierarchy variable. And so if you look at the evaluators, it will show here that it's a field using hierarchy. And if yours doesn't for some reason, then you're probably using the wrong network data set, such as the walking one, for example. So you have to go back and close that and make sure you're using the right one. Next, we could also look at, for example, the minutes or meters in this case. So meters is using road length in meters. And that'll automatically, again, be found for you. Next, minutes, the time attribute, which is fundamentally important to driving, usually more important than distance. So it'll be the default. And it will find the fields FT minutes and TF minutes, and just minutes as well for the turn feature class. Automatically found again, but you should always check it out. You got to make sure, of course, that's part of the validation, right? Validating stuff is to make sure that what you see there is behaving the way you expect it to. And so when you create that data set, you always need to check the evaluators for these variables that will be used to make sure they're picking up the right things. Then we can also add another attribute called a descriptor such as speed limits. So we do have a column that is the speed in kilometers per hour for each road, but we can also add that just as a descriptor for the network. And so we call it speed limits. We choose descriptor. It's not a cost. And descriptors are things that describe segments or edges in the network, but do not depend on the length of things, the way time does, for example. So there's something that applies to the whole edge, but is non-dependent on distance. Speed limits, you could put the units in kilometers per hour if you want, and the data type will be double. It'll pick it up from the field. So that's, but you should choose double here if it's not chosen by default. Once you add that, it'll show speed limits here, and then you click on evaluators and make sure it's choosing field SPD _ kilometers, values for the from to and to from. And that's it. Oh, actually, there's a couple more things, isn't there? So for the travel mode, you just skip that. Like you see here, there's nothing there, so skip. Then, do we want to establish driving directions? Yes. So this will be used for driving directions potentially because it's a road network for driving. We want to build the service area index by default, speed up other calculations later. And then we get our summary. You can copy that to some document so you know what you chose in case things don't operate the way they should. And then you click Finish. Our second example is called closest facility analysis. The idea of a closest facility analysis is very simple. You have locations in space and you want to find the closest facility to those locations. A facility could be a hospital, a clinic, it could be a waste depot, it could be anything in space to which you want to travel to from some set of locations within space. For example, finding the closest hospital based again on the network distance to a traffic collision incident. So emergency vehicle routing, for example, is also an application for closest facility analysis. The first example we'll do with the driving network is called a closest facility analysis. For a public health seminar on COVID-19 messaging at hospitals, Ottawa Public Health wants to assign physicians to the seminars they'll be holding at the hospitals and assign the physician offices according to the closest hospital location to the physician office. So each physician has to be assigned to the closest hospital in terms of travel time for these seminars on COVID-19 messaging. So to do this, we need to know the physician locations and the hospital locations, like you see here on the little map. And this is called a closest facility analysis because we're taking what are called incidences. An incidence is something in space that we want to find the closest facility for, where facilities here are hospitals. Is the hospital, and the incidences are the clinics or physician offices. And so each physician office needs to be assigned to its closest in driving time, not in geographic distance, like this. I'm just showing, for example, we need to assign that to the closest hospital in terms of time. And that's called the closest facility analysis. And the names of the network classes are facilities and incidences. And remember, facilities are always the things you want to go to, and incidences are the things you want to go from. So we create a closest facility analysis layer in the Analysis tab, Network button. Then we end up with the closest facility analysis layer right here. And it has the classes facilities and incidences. These are required. So those are required things that must have locations on the network. Otherwise, you can't run this type of an analysis. So the first thing we do is import the network locations to the facilities class right here. And we do that with the import facilities button on the closest facility tab for the network group tab. So you have to make sure you select closest facility or you won't see that tab come up for closest facility. So then you click on import and up comes the regular add locations dialog. So there's nothing new here from before other than the naming of things and what we put into facilities. So closest facility, sublayer, the first one is facilities, and it knows that because we clicked on import facilities. So we just have to choose the hospitals layer. And again, that's in the same feature data set, hospitals. Then we can choose a field name for name. And this is important because that'll be carried over into the analysis so that we'll have the name of each hospital in the new attribute table for closest facility that will be produced. Then our regular 200-meter search tolerance. You can also put a sort field here. It's not necessary, but I just like to have it sorted by name, so it's alphabetical in this case. Since the physician, I shouldn't say the physician, but the hospitals are all sorted alphabetically. Their names are. Since it's the first time I'm loading, I can keep the append to existing locations on. Snap to network as usual, and then you click run. And that will load in the hospitals as the facilities, the things that we want to assign other points in space to according to closest time. Then we look at import incidences. Again, add locations, and it will fill in the closest facility and incident sublayer or class. Input locations this time are physicians because we're assigning physicians to the facilities. We need to know for each physician the closest facility. And this loads into the incidences class. The reason it's called incidences is often this is the type of thing that's used in routing, let's say, emergency services, where you might have an incident taking place somewhere or multiple incidences, and you need to route a, let's say, a emergency vehicle to the closest facility that can handle that type of an emergency situation and stuff like that. So the naming kind of comes from there. But it's not obviously limited to that. This is a general approach to assigning things on the network to other things on the network, whatever you want incidences or facilities to be. So we're loading physicians in this case as the incidences. And we choose here for name, the physician ID, and that will pair up later with the name of each hospital. So we want to be able to see, of course, which physicians go to which hospitals. So we need to have something that identifies the physician and the hospital paired together. So we know who's going where for the seminars. Again, nothing new down here. And we click run. Next, we set up the analysis before running it. Now that we have loaded our classes, both the incidences, which are the physicians, and the facilities, which are hospitals. Now we want to say towards facility because we're routing things from physician to facility. So it's the travel time to the facility that matters in figuring out the closest hospital for each physician. And what do we want to find? Well, we want to find the one best facility or closest facility in terms of time for each physician location. So we put a 1 here. If we wanted to find the first 2, then we would put 2 there, and then we would find the 2 closest hospitals for each physician, or 3 or 4, all the way up to n facilities. So we have 8, for example, so we could put a maximum here of 8. And then we would have, well, all 8 and the time it takes to travel from each physician to all 8 of the facilities. The next thing is the output geometry again. So in this case, the output geometry could be nothing, because we may only need a table. And the output geometry doesn't actually do anything except produce a visual representation of this optimal routing in the network to each facility from each physician office. So if we want to see that routing or the actual lines in the network, we would choose a long network, but that takes longer to compute. No matter what you choose here, the solution will be based on the network itself. So it'll follow the network from each physician to the closest hospital in terms of time along the network. Even though it may not be represented by anything on a map, or it could be represented by straight lines, or it could be represented by the actual paths themselves, right? Now, the reason a long network takes longer to compute is because it has to make a whole bunch of geometries in the solution, rather than just doing the algorithmic computation to find the closest facility for each physician. It will have to also compute and create geometries that follow the network, and that takes time to compute. Straight lines are quicker to compute and still give a visual, and actually a better visual assessment of which physicians are going to which locations. Visually, it'll just put a straight line on the map to represent that network distance, or actually not to represent the network distance, but to represent which physicians go to which facilities, and a straight line will be drawn from the physician to the facility, even though the actual solution was based on a network distance. It just represents those graphically as such. So I like to use the straight lines. You can choose a long network. It'll just take longer to compute, that's all. Straight lines are just quicker to compute, and they give a much better visual portrayal of the routing. And you click run. So the result would look like this. Here's an example. So in this example here, I chose 8. So I chose to choose all 8 of the facilities. If you followed the slide previously, you'll just do 1, which is fine. But I chose all 8. And then, for example, here I'm just highlighting the Sisters of Charity Hospital. And there's a bunch more up here too, you don't see. So Sisters of Charity Hospital, right here, near the river, has a whole bunch of physicians routed to it. And the shape length is given here as an example. And then the time as well. The total time will be in a field next to that, etc. But what it shows then visually then is what you see here. This is the example. The Sisters of Charity Hospital is right there in the middle, in the center of all that action. And each of the physician offices are just connected to that with a straight line. And it shows very clearly visually which physicians are routed to this hospital versus, let's say, this one over here, versus this one over here, or this one. And when you see stuff like that, of course, you'd have to go in and probably say, well, I'm going to choose one of these 2 hospitals, not both of them. It doesn't make sense to hold a seminar for 3 physician or 3 clinics. So I'd probably want to have those routed over here, or depending on the hospital type and its capacity, all those ones routed over here. And that means removing one of those features from the facilities layer. And so that's the solution to that. And the important thing is this attribute table, which assigns the physicians to the particular hospitals. And so I said I used all 8 there. I didn't. This is actually just one. So I didn't choose all 8 there. I didn't mean to make that sound a bit confusing. This is basically exactly what was on the previous slide. So I chose the closest, just the one closest for this analysis. I was thinking of another analysis for some reason. So that's closest facility analysis. And in the name field of the output line layer, so the output layer is just called lines, and it will either be looking like this, or it could be looking like nothing if you chose no geometry as output, or it could be the actual, from each of these, the actual network distance to get there, not the distance, but the network paths, and it just makes it more confusing visually when you try to look at it if it's not lines. So that's why I chose lines as the output. That being said, the name field is important because this combines the physician ID with the name of the hospital. So we then know the physician identifier for each hospital. And that's the important thing we wanted in the output, was that combination of things, because that's routing now, or tells us which physicians will be assigned to each hospital. And you can see that here. This is the physician ID combined with the name of the hospital. And it's that field which is important for the actual final output, because then you know who to assign where.